Hi guys, in the previous video we saw that why do we need dynamic programming in order to solve this problem of finding an optimal binary search tree. And in this video we are going to solve an example of finding the total cost of an optimal binary search tree and the structure of an optimal binary search tree when you are given a set of keys with the corresponding successful and unsuccessful search probabilities. So if you have not watched the previous video, I'll recommend you to go and watch it so that you can get a better intuition that why we are solving this problem of optimal binary search tree using the method of dynamic programming. So let us solve this example of finding the optimal binary search tree using dynamic programming. This is actually the question and we are given 4 keys over here. So this is a 4-node binary search tree. And the successful and the unsuccessful search probabilities are also given. We have seen this formula of dynamic programming. We have also seen this third formula and this formula also we have seen. So basically earlier I said that Wij plus 1 is equal to Wij plus Pj plus 1 plus Qj plus 1. So if you clearly see that both these things are actually the same. So there is no difference between this and this. In this case, only instead of j plus 1 is substituted over here, and instead of j minus 1, actually j is substituted over here. Otherwise, both things are actually same, right? So just to clarify. So now, let us try to find the solution of this problem. So first, I want you to tell me that will we start from here of finding the cost of a 4-node binary search tree or finding the cost of a 0-node binary search tree. But before that you need to remember that actually when j minus I is equal to 0, in the case of Ci comma j, when j minus I is equal to 0, that means it is a 0-node binary search tree. In the same way, this is a 1-node binary search tree and this is a 4-node binary search tree. So all these binary search trees in the first row are actually 0-node binary search tree. So should we start from here or from here? If you would have understood the previous explanation clearly, you will tell me that actually we should start from here, because to know the cost of a bigger binary search tree or a binary search tree with greater number of nodes, we actually need to know the cost of the smaller binary search trees or the subtrees, right? So for that we need to start from here, right? Because if we start from here, we actually need to know these things to solve this thing, right? So again it will lead to over calculation, so we start from here. So for a 0-node binary search tree, what is the cost of 0, 0? When there are no nodes, obviously the cost will be 0 of that binary search tree, and of course in this case also there are 0 nodes, so the cost will be 0. So here also the cost will be 0. All these are 0-node binary search trees, so obviously there will be no cost, right, pertaining to these trees. And what about the root? What will be the root of a binary search tree in which there is no node? So there is no root, so instead of that we write 0. Okay, now for finding the weight of a 0-node binary search tree. So if we use this formula over here, the third formula, you will understand that actually this summation in the third formula is actually not present. The reason being that our lower bound is actually starting after our upper bound. So this summation actually vanishes, right? So there will only be left with one term when we are considering a 0-node binary search tree. So basically W of I comma I is equal to, or W of I comma j is equal to Q I when I is equal to j. If you have understood this, well and good. So here here it is Q0. So W0 will be equal to Q0. So that is Q0 is 2. W11 will be equal to Q1, 3. W22 will be equal to Q2, that is 1, and this is also Q3 and Q4. Okay. So now we have done the calculation for the 0 node binary search tree, right? These are 0 nodes binary search trees. Now let us talk about the 1 node binary search trees. So if we try to find out the cost of C 0, 1, so C 0, 1 using this formula will be equal to minimum of I, what is I? 0 less than K less than or equal to J, which is 1 over here. So this will be basically C I is 0, K minus 1. So what is the value of 1? How many values K can take over here? Only one value, which is 1, right? It cannot take 0. So K over here, K minus 1 in this term will be 0 because the value of K is 1, and this will be equal to C, K is 1, J is actually 1, right? Plus there is another term W of I comma J, so W of 0 comma 1. Okay. So we understood that this is actually the calculation of C 0 comma 1. So if we solve it further, minimum of what is C 0 comma 0? Have we found it out? Yes, it is 0. What about C 1 comma 1? Again, if we think about it, it is a 0 node binary search tree. So the cost of a 0 node binary search tree will be 0, and that is what we will find it over here, right? What about the weight of 0 comma 1? So through this we are understanding to find out the cost of a subtree. It is first of all important to find out the weight of that subtree, right? And to find out the weight, we actually need to look at the successful and unsuccessful search probabilities. So before finding out C 0 comma 1, I actually need to find out W 0 comma 1. So we will follow this strategy in every case. First of all, we will find out the weights, and then we will move to the cost, because we know that the cost is actually dependent on the weight, right? So first we will determine the independent property. Okay. So W 0 comma 1 according to the third formula will be equal to Q0 plus P1 plus Q1. I guess you can easily understand this if you use this formula, right? So what is Q0? Q0 is 2. And what is P1 and Q1? 3 and 3. So 3 plus 3. So this is actually equal to 8. So we found out W 0 comma 1 is 8. And for the time being, we have found out W 0 comma 1. We can substitute over here. So this is minimum of 0 plus 0 plus 8. I'm solving for C 0 comma 1. So this will be equal to 8. So we have found out C 0 comma 1 also as equal to 8, right? Okay. So actually in this problem we saw that the weight, so while doing this calculation we understood that the cost of any binary search tree is actually dependent on its weight. So let us first find out all the weights. Okay. So if you want to find out the weight of W1 comma 2, what do you think will be the weight of W1 comma 2? Rather than using the third formula, if we use the second formula, you will understand that W1 comma 2 is actually equal to W1 comma 1 plus P2 plus Q2. Am I right? If you use this formula. So basically W1 comma 2 is equal to W1 comma 1 plus P2 plus Q2. So that is equal to 3 plus 3, 6 plus 1, 7, right? And in the same way, W2 comma 3 will be equal to W2 comma 2 plus P3 plus Q3. So what is W2 comma 2? 1 plus P3. P3 is 1 plus 1. So that is equal to 3, right? 1 plus 1 plus 1, right? So now what about W3 comma 4? It will be equal to, yes, W3 comma 3 plus P4 plus Q4. So W3 comma 3 is 1 plus 1 plus 1. So this is 3, right? So in the same way, how we found out these weights using the above weights, in the same way these weights we can find out again using the second formula rather than the third formula. So basically W0 comma 2 will be equal to W0 comma 1 plus P2 plus Q2, right? Using the second formula. So W0 comma 2 will be equal to W0 comma 1, that is 8, plus P2, that is 3 plus 1. So 4 plus 8, that is 12. So W1 comma 3 will be equal to W1 comma 2, that is 7, plus P3, 1 plus 1, that is 2. So 7 plus 2, 9. And W2 comma 4 will be equal to W2 comma 3, that is 3, plus P4 plus Q4, that is 5, right? 3 plus 2 is equal to 5. In the same way, W0 comma 3 will be equal to, now you will have to actually expand this W0 comma 3. So it will be equal to, you can obviously say that W0 comma 3 is actually equal to P0 plus P1 plus Q1 plus P2 plus Q2 plus P3 plus Q3. But rather than that, why not use this formula, the second formula, and say that W0 comma 3 is actually equal to W0 comma 2 plus P3 plus Q3, right? Because we already have the value of W0 comma 2 and there will be less calculations, right? So W0 comma 3 will be equal to W0 comma 2, that is 12, plus P3 plus Q3, that is 1 plus 1, 2, so that is 14. And W1 comma 4 will be equal to W1 comma 3, that is 9, plus P4 plus Q4, that is 2. So 9 plus 2, 11. What about W0 comma 4? So this is the last weight. W0 comma 4 will be equal to W0 comma 3, that is 14, plus P4 plus Q4, that is 16, right? So we have found out that the weight of our optimal binary search tree will be equal to 16. So now let us do the calculation of the cost and the root. So now let us find out the cost of 1 comma 2. Now it will be much easier because we know the weight of 1 comma 2. So cost of 1 comma 2 is actually equal to minimum of 1 less than k less than or equal to 2. So this is C 1 comma 1. So k over here can have only one value, which is 2, plus C 2 comma, what is j? J is actually 2, plus W of I comma j, so W of 1 comma 2. So do we know W of 1 comma 2? Yeah, we know this is 7. And what is C of 1 comma 1? So if we write it, minimum of C of 1 comma 1 is actually equal to 0, and plus C of 2 comma 2, again 0, plus 7. So this value is actually minimum of 0 plus 7. So this is C 1 comma 2 is 7. Okay, so the C 1 comma 2 is 7. As you can see, for the one node binary search tree, we are actually getting the cost equal to the weight of that binary search tree. So let us write it down for the rest of the trees as well. If you think deeply, you will actually understand that why the cost of a one node binary search tree is actually equal to the weight of that binary search tree. If you have already understood, please write it down in the comments. So now how we will find out the root of these binary search trees, like R0, 1, R1, 2 and others, how we will find them out? So basically, root of a binary search tree, we can find it out by looking at the minimum value of k, or to put it more clearly, by writing down that value of k as the root on which we got a minimum term. So in all these cases, we are getting only one value of k. Here we were getting only one value of k, that is k is equal to 2 in the case of C1 comma 2. And over here we were getting only one value, that is k is equal to 1. So they themselves will be the root because we have no other option. So this will be, here root will be 1, here 2, here we would have got 3 and here 4. If you have any confusion, you can try to solve these yourselves, right? And then you will understand them better. So now let us look at the two node binary search tree. So to find out, let's find out the cost of C0 comma 2. So for C0 comma 2, minimum of 0 less than k less than or equal to 2, C, I is 0. So what will be the values of k over here? K is equal to 1 and 2, right? So for k is equal to 1, 0 comma, k minus 1 is, so here k is equal to 1, so k minus 1 is 0 plus k is 1 comma 2. So this is the first term where k is equal to 1, right? Now for the second term where k is equal to 2, so C 0 comma 1 plus C, k is actually equal to 2 comma 2. Okay, so plus W 0 comma 2. Okay, so now let us find out this minimum term. So minimum of, what is C 0 comma 0? We know it is 0 plus C 1 comma 2, C 1 comma 2 is 7 comma, then C 0 comma 1, C 0 comma 1 is 8 plus C 2 comma 2, of course it will be 0 because it is a 0 node binary search tree, we don't need to look at the table, plus W 0 comma 2. What will be W 0 comma 2? Do we know it? Yeah, we have already calculated the weight values, now it is helping us, right? So plus 12. So this will be, what is the minimum? 1 is 7, 1 is 8. So this is actually minimum, right? So this is 7 plus 12. So we have got it as 19, right? So this cost is actually 19. And at what value of k did we get the minimum term? We got it at the value of k is equal to 1. So that is why our root will be equal to 1. We got it at the first term, right? And at that first term, the value of k was 1. It was not 2. So that is why we have written the root as 1. Now I want you to solve for cost of 1 comma 3 and cost of 2 comma 4. So these are the values that you will get when you will solve by yourself. I request you to solve it by yourself. And now let us solve for the 3 node binary search tree. So let us try to find out C 0 comma 3. Right? So according to this formula, it will be equal to minimum 0 is less than k less than or equal to, what is j? J is 3. And so what values k will have? K will be equal to 1, 2 and 3. It will not be 0. So when k is equal to 1, so we will have C, I is 0. So 1 minus 0 is 0 plus C1, 3, right? So this is when k is equal to 1. So now for k is equal to 2, I is 0. What is k minus 1? K minus 1, when k, here we will do k is equal to 2 and here we are going to do k is equal to 3. So when k is equal to 2, k minus 1 is actually equal to 1 plus C 2 comma 3. In the same way, here it will be 0 comma 2 plus C 3 comma 3. Okay. Plus, after this we also need to add the weight, which is W 0 comma 3. Okay. So now, what is C 0 comma 0? It is 0. Okay, so what is C 1 comma 3? C 1 comma 3 is 12. So 0 plus 12. And for k is equal to 2, what is C 0 comma 1? It is 8. What is C 2 comma 3? It is 3. And what is C 0 comma 2? So C 0 comma 2 is 19. And C 3 comma 3 is actually equal to 0. Plus weight of 0 comma 3. So what is weight of 0 comma 3? It is 14, right? So this will be plus 14, right? So minimum, so let us first solve for these minimum terms. So 12 comma 11 comma 19. Of course, this is the minimum because here it is 11. So this is 12, this is 11 and this is 19. So at k is equal to 2, we are getting the minimum, right? Yes, at k is equal to 2, we are getting the minimum. So we have already sorted out our root in our heads, and that will be 2. But what about the cost? Cost will be equal to 11 because it's minimum plus 14. So that will be equal to 25, right? So the cost will be equal to 25. So in the same way, you can solve for this cost of 1 comma 4. So here again for cost of 1 comma 4 we will get 19 and the root we will again get it as 2. Okay. So now let us solve this finally cost of 0 comma 4, that is what we require in the question, and we have already got the weight of 0 comma 4. So let us now solve the cost of 0 comma 4. C 0 comma 4 is equal to minimum of 0 less than k less than or equal to 4. So obviously k will have 4 values, that is 1, 2, 3 and 4. Okay. So here we will write when k is equal to 1, k is equal to 2, k is equal to 3 and k is equal to 4. So here we will write down those terms. So let us start writing them down. C 0 comma, what is k minus 1? 0 plus c 1 comma 4. And when k is equal to 2, c 0 comma 1 plus c 2 comma 4. Right? I'm just using this formula. C 0 comma k is equal to 3, so this will be 2 plus c 3 comma 4. So here c k is equal to 4. What is I? I is 4 and the here k minus 1, so 3 plus c 4 comma 4. Right? Plus w of 0 comma 4. Right? We shouldn't miss the weight. So what will this be equal to? Let us try to minimize these terms. So let us try to find the minimum out of all these terms. So what is c 0 comma 0? It is 0. And what is c 1 comma 4? So c 1 comma 4 is 19. Right? What is c 0 comma 1? c 0 comma 1 is 8. And c 2 comma 4 is 8. Right? Then what is c 0 comma 2? It is 19. And what is c 3 comma 4? c 3 comma 4 is 3. What is c 0 comma 3? It is 25. And what is c 4 comma 4? No need to check, it will be 0. Okay. Plus w of 0 comma 4, it is there written 16. Okay. So now minimum of this is 19 comma 16 comma 22 comma 25 plus 16. So the minimum we are getting over here, so that is equal to when k is equal to 2, right? At the second term we are getting the minimum. So this is actually equal to 16 plus 16, that is equal to 32, right? So the cost over here is equal to 32 and the root will be 2 because at k is equal to 2 we are actually getting the minimum value, right? So now we have completed this table, right? We know the cost of our optimal binary search tree, which is 32, but now there is a catch. If you would have paid attention at the starting itself, you would have understood that actually all these are probabilities, this 3, 3, 1, 1, and you know very well that the probability lies only between 0 and 1, it cannot be 2, 3, right? And the sum of all these probabilities should be 1. So for the ease of our calculation, we actually took these numbers. So if you sum this up, it will be equal to 16. So basically these numbers, all the probabilities are multiplied by 16. So basically the value over here was not 1, it was 1 by 16, right? So that is why the cost that we will get will also be multiplied by 16. So that cost, final cost, we actually have to divide by 16. So our final cost C0, 4 will be equal to 32 by 16 because initially we did the multiplication of all the probabilities by 16 for ease of calculation. So this will be equal to 2. So our final cost of our optimal binary search tree, out of all those 14 trees, there is actually one optimal binary search tree and its cost is 2. But one thing is still left. We know the cost of the optimal binary search tree, but we don't know how does our optimal binary search tree looks like. Does it looks like this? Or does it look like this? We don't know. It can be any one of them or the other 12 out of other 12. So can we find out the structure of our optimal binary search tree through this table? Yes, we can. So this is our optimal binary search tree and its root is 2. That is what we know. So if we do the numbering over here, this is 1, 2, 3, 4. So we know that the root of our optimal binary search tree is actually 40 because the second key is actually 40. So at the top we will have 40. This is what we know, right? And another thing that we know is that because it is a binary search tree, so the value of 20, which is less than 40, will be obviously on the left side of 40, and these two values that are 60 and 80 will be on the right side of 40. We don't know their exact positions. Okay, so basically this was 0, 4, the range of 0, 4. It got divided in this way that it became 0, 1 and 2, 3 and 2, 4. And became 0, 1 on the left and 2, 4, right? So now do we have a cell for 0, 1? So now do we have a cell for 0, 1? Yes, we do. And what is the root over there? 1. But we don't, in this case, yes, the first root is 20. So even before we knew, so even without looking at the table, as there is only one node over here, we can understand this node will be 20. But what about these two nodes? Which will be the parent and which will be the child? So what about, do we have a cell for 2, 4? So yes, there is this cell of 2, 4. And from that, there it is written that the root of 2, 4 is actually equal to 3. So the third node is the root. So that means 60 is the root, right? So we know that 60 will be the root. Okay. So now, because it is a binary search tree, you can obviously draw 80 over here rather than making it the left child. But again, this will be divided into 2, 2 and 3, 4. So if do we have a cell for 3, 4? Yes, we have, and its root is 4. So you will come to know by itself that the fourth node will come on the right side of 60, and that is 80. So this is basically the structure of your optimal binary search tree, right? So this is your optimal binary search tree, right? So in this video, we didn't only find out the optimal binary search tree or the structure of the optimal binary search tree, we also found out the cost of that optimal binary search tree, that is 2, right? So in the next video, we will actually see the next advanced data structure, that is the red-black trees. That's all from my side. See you in the next video.